Welcome to lesson 2.3 on relative motion. Now, first, when we talk about relative motion, it's probably a good idea to say that. And this is really the motion observed with respect to an observer. Observer. So, when we talk about ground motion, what we're really talking about is the ground as being the uh, reference point for the observers. So this is motion seen in reference to a person on the ground. So typically, an observer on the ground is watching something. Now, if it's on the ground, it's tends to be only that one vector that we're dealing with. But when we're talking about relative motion, we're really starting to now add two vectors. And so we've got the velocity from the air or boat and the velocity from the wind or the current happening at the same time. And so this is the uh, velocity the planar boat moves without any other vectors. Without help, right? Or a hindrance, really, but without something causing it to change. What could cause that change? Well, this is a wind or current. And so this is an additional vector, which which affects the motion. Now, when we say it affects the motion, really, again, this is dealing with respect to the ground. And so it's a ground motion that it's doing. And so really, relative motion is the addition of two vectors. Now let's just take a quick look. Uh, this is kind of from last time. If we had an observer on a glass train, now it's moving so we've got a glass train moving 25 meters per second forward, right? And we've got a person here on the ground, and she's looking at a ball. Now, a person on here throws a ball also 25 meters per second forward. Well, the ball is moving towards this end at 25 meters per second, as the glass train is also moving 25 meters per second. And so the velocity of the ball with respect to the ground would actually be 50 meters per second. Now, what happens if that glass train is moving again forward with 25 meters per second, but the ball is moving 25 meters per second in the opposite direction? The person on the ground would actually observe this to be traveling at 0 meters per second. I'm going to just put up a clip here to kind of show this idea of uh, canceling velocities. So what's happening here is we've got this cannon that's being shot out of the back of a truck as it's moving along, and they're just watching this as this is moving along. Now, they're trying to shoot this ball at the exact same velocity backwards as it's moving forwards. And as we can see, the ball does not move with respect to the ground. Right? Took a little bit of finagling, but they were able to do it. Okay. Now, where most students get confused with this is to uh, try to keep the situation clear, because typically you've got several vectors, but really this comes down to an adding vectors questions. You're always adding vectors, and we're doing it within 2 dimensions. And one of the tricks that I usually find is to draw the resultant first. Draw the resultant first. Based on the scenario, right? Based on the scenario, we'll draw the resultant first, usually with the dash, and then we've got to make the other vectors come together to make that resultant, because intuitively, this one, people are usually pretty good at figuring out what this one should be. But they get all confused with some of the other things and they start drawing them. The resultant should be tip to tail addition of the other two vectors, one of which is that air or boat velocity, right? And the second one being the wind or the current, which way the wind or current is taking the air or the plane or the boat off course, shall we say, assuming that this is there. And so we see that resultant of two vectors. So, for example, if a plane flies with an airspeed of 789 kilometers per hour, find the direction the plane will have to fly to compensate for a 45-kilometer north wind if it is traveling due east. Okay, so first thing we're going to do is traveling due east, which means that the results of our vectors needs to be this, traveling due east. This is the result. Now, this is the result of both the plane and this wind that's going in a north direction, right? So we've got wind going north. The plane is going to have to be coming like this. This is the wind, and this is the plane or the airspeed that's making that result. We're looking for this direction. We know that this is 789 kilometers per hour, and we know that this is 45 kilometers per hour, which means this wind is the opposite side and the airspeed is the hypotenuse, so we're going to use sine, opposite over hypotenuse. We're going to be looking for that angle of 45 over 789. And so as we solve for this, you're going to find that the angle is in fact 3.3 degrees. Now, based again on the way that these vectors are moving and the way that we drew them, this is going to have to be south of east. Now, part B asks us, what is the speed relative to the ground? Well, our result, we know again this was 45. We know this is 789. So what we're really looking for is this side. Given the fact that this is drawn as a right triangle, means that we can simply use Pythagorean theorem. Now, c squared is equal to a squared plus b squared. This is your side C, the airspeed. This could be A or B. We'll call it A for the wind. And so side B is both of them together. C being the hypotenuse, so we're going to take c squared minus a squared is equal to b squared, or 789 squared minus 45 squared is equal to b squared. That gets you a 787.7 kilometers per hour as being both of them together. And that's not unexpected. This is a rather small angle of only 3.3 degrees. And so we are seeing that we're not being dragged too much off course, even with a 45-kilometer wind. So how long will it take for the plane to travel 200 kilometers? Well, we've got a 789, a 45, and a 787.7 kilometers per hour. The one that we're really worried about is the resultant. This is what it's actually traveling with respect to the ground. And this 2,000 kilometers is a distance with respect to the ground. So, given that v is equal to d over t, or time is equal to the displacement divided by the velocity, that velocity is 787.7 kilometers per hour. Wait, that's a velocity. My mistake. Distance over velocity. Well, the distance or displacement is 2,000 kilometers divided by 787.7 kilometers per hour. We're looking for time. So that time is going to be 2.538 hours. And yeah, I know it goes on and on and on. Which really means 2 hours and if we want to figure out the 0.538 in minutes, we're going to multiply just the decimal by minutes, and it's actually 32 minutes. Okay, moving on to our next one. So we've got a pilot of a small plane needing to transport 2 people on an airstrip 300 kilometers due west in 2 hours, right? So it's traveling due west 300 kilometers over 2 hours, which means it needs to be traveling at a speed of 150 kilometers per hour. Now that is the result. That's where it has to go. We are here and we need to get to here in 2 hours. But there is a wind, and the wind is blowing at 48 kilometers per hour, 65 degrees north of west. So 65 degrees north of west, and it's a 48 kilometer per hour wind. Right? This is our result that we drew first. And so the plane is going to need to come this way. Now, if you recognize this triangle as simply being 150, 65, 48, and we're looking for this side, well, then you can use the cosine law. If you are unfamiliar with the cosine law, we are going to do this with vector addition. And so we're going to break apart this 48 kilometers per hour into its components. Right? So let's take a look at this one specifically, this 48 kilometers per hour. It's 65 degrees. We're looking for the components in the x and y. Okay, so to find the x side, that's going to be 48 cosine 65 to find that x amount. And that is 20.3 kilometers per hour is the x. And 48 sine 65 is equal to that y, which gives us 43.5 is equal to that y component. So now we move to the plane. The plane is moving down like this, but we know because this result is moving completely west, that this y component has to be the y component of the plane. So this is 43.5. The y component is 150 kilometers per hour minus the 20.3, because that's already part of what the wind is actually carrying us. And so this here is going to be 129.7. And again, we get that from taking the 150 minus the 20.3. We've now got our components, and we now need to find our velocity using Pythagorean theorem and find the angle using tan. Okay, in this case here, looking for this angle, well, actually, let's look for c squared is equal to a squared plus b squared using Pythagorean theorem. That's 129.7 squared plus 43.5 squared. That is going to get you 136.8 kilometers per hour. And at an angle of, we'll use tan of an angle of opposite over adjacent, that's the 129.7 over 43.5. That gets you an angle of 71.5 degrees. And so putting this together to two digits is going to be 140 kilometers per hour at 72 degrees, and that is going to be west of south, based on the way we've drawn this, west of south. Now, if you would have done this 18 degrees south of west, would have been just as sufficient. Okay, moving on to example number 3. We've got a paddle boat. Little error there. A paddle boat traveling north on a river with the speed of 9.26 kilometers per hour, which is also 5 knots, by the way. If the boat's velocity to the ground is 10.4 kilometers per hour, 20 degrees east of north, what is the velocity of the current? Well, in this case here, paddle boat is traveling at an angle of 10.4 kilometers per hour, and it's 20 degrees east of north. Now, we need to figure out what's happening with this current. It's traveling north. This boat is traveling north at 9.26 kilometers per hour, and we've got this component. Now, we don't know if it's exactly east or whatnot, but we know it's going to be in somewhat of an easterly pattern because the boat is traveling east. We're told that this is going due north. And so we don't know the components here, but we need to figure out the components of this piece here, given the hypotenuse and the spot that's going exactly north. So what we're going to do here is we'll break down this into components, the final velocity into its x and y components, so that we can figure out what's happening with this last piece of current. Okay, so to find the x component of this, that's the same as 70 degrees here. Okay. Now we could do this. Actually, let's do this with the original 20, just so that it is clear. It is 20 degrees, this being 10.4. This will be our what? Oh, what's happened here? I have moved all over the place. Okay, this will be our y component, and this will be our x component. Our x component is going to be 10.4 sine x, and our y component is going to be 10.4 cos 20. X is equal to y. So finding this x component, this x component is 3.55 kilometers per hour. This y component is 9.77 kilometers per hour. Now, taking a look here, this y component is a little bit longer than what the boat was capable of traveling. In fact, the current is taking us with a northern component of 0.51 kilometers per hour in a northern component. We have that easterly component of 3.55 kilometers per hour, and so now we're just looking for our final answer. Using c squared is equal to a squared plus b squared, we're going to take the 3.55 squared plus 0.51 squared. C is 3.6 to 2 digits, right? Because we've got this 20 here, we're going to just go to 2 digits. To find the angle, we're going to use tan. 0.51 over 3.55, and that angle is going to be 8.2 degrees. Now, based on the way we've drawn this, it is north of east. Okay, I'm hoping that helps. If you do have any questions, let me know.